Hi, everyone, and thank you for waiting. We will now get started with this webcast. So today's webcast will be presented by Miguel Castro, who is a PhD student at the Anybody Research Group at Aalborg University here in Denmark. So in fact, both of us are sitting here in the same room in Aalborg. I'm your host. My name is Anant, and I work as a product specialist for Anybody Technology, which is the company that actually makes the Anybody modeling system. So Miguel works for our sister research group at the local university over here. So just to give you a quick overview of how things are going to proceed, we'll start with a quick introduction to the Anybody modeling system for those of you who are new to this software. This will be followed by Miguel, who will give us the meaty details of today's talk. He'll start by talking about kinematic measurements on the 3D reachable workspace, and then he'll also talk about experimental force measurements. That is the force production capability in different directions when you're sort of reaching out in different directions. And then he will talk about how these measurements can be used to actually validate a musculoskeletal model. And we will finally follow this up with some questions and answers. So just a quick introduction to the Anybody modeling system. So it's a simulation software, and the class of simulations that it performs, they're called musculoskeletal simulations. Now, the inputs to these simulations are motion data in the form of motion kinematics and external forces acting on the body during motion. And the outputs are the body loads, the internal body loads, such as the joint moments, the muscle forces, and the joint reaction forces. So as for applications, we see our clients using this technology in a variety of fields, which range from product design optimization to ergonomics, planning the outcome of surgery, generating load cases for finite element analysis. So in case you're trying to make an implant and you would like to get realistic loading conditions for the implant under when the person's doing different types of activities, you can again use these simulations to generate those load cases. And last but not the least, just plain and simple, good old motion analysis. To give you a little more detail into how these simulations work, as I mentioned in the previous slide, there is the motion and forces form the input or form one of the inputs, and then you have the human body model, and you then also have a model of the environment. Now, this is something that you may or may not use depending on what exactly you're trying to achieve. So in this case, the environment is an exoskeleton for the lower part of the body. And you combine all three of these into a single man-machine model and then run an inverse dynamic simulation. So this is the type of simulations this is the class of simulations that Anybody runs. And this has a muscle recruitment algorithm, which essentially gives you the instantaneous values of your different body loads, such as your muscle forces and your joint reaction forces. Now, these forces may be the end products that you're looking for, or you can pass it on to other post-processing tools such as FE software. Or in some cases, you may actually want to optimize the design of your environment so that you get some favorable biomechanical outcome for the person wearing it. So for example, if you had to design this particular exoskeleton so as to reduce overall metabolic energy expenditure, then you could probably run these optimization studies inside the Anybody modeling system as well. So you essentially parameterize, you define the exoskeleton by a set of design parameters, and then you tweak those design parameters until the required outcome, biomechanical outcome, is achieved. So on that note, I will give the word over to Miguel.
Okay, perfect. So as Anant already introduced me, I'm working with John Rasmussen, Xiao Pingbai, and Michael Skipper-Andersen, my supervisors, at the Department of Materials and Production at Aalborg University. So today we're going to talk a little bit about half of my PhD project, so to speak, regarding the validation of musculoskeletal models using the reachable workspace. So the background for this project is that as an end goal of my project to give life back or independence to people who suffer from impairment, physical impairment, and cannot perform their daily activities at home. We're looking for designing an exoskeleton. So we already did it. And during the process, resorting to musculoskeletal models would be one of the possibilities to help designing a better solution that fits a given subject. We must bear in mind that what we want is to make a subject-specific device in the end that fits precisely the needs of that specific user. So we would like to also to answer that question, whether we can use musculoskeletal modeling to improve these designs we perform. So here I'm showing you the workflow for my project. I've been working on this for 3 years, for the past 3.5 years, and this workflow mainly shows what are the goals of this project. Today, I will only be focusing on the modeling part because that's a little bit extended. So we should focus for that now, and maybe in another occasion I'll also present the other half. So subject-specific model, we will look into acquiring user data in order to have better representing models. Ideally, would love to have a model that really represents that subject we are trying to simulate. And if that's the case, then we would expect that any experimental data we can collect from an original subject, then the model would be ideally able to replicate it. However, that's not entirely true yet, but we are moving forward to that point. So first of all, what is the reachable workspace? So if we think of robotics and manipulators used in robotics, typically the reachable workspace is a region or a volume that is defined by all the positions that the end effector of that machine can reach or can be positioned with at least one orientation. So if we think of the human arm, so the human upper extremity, in the sense of a manipulator tool, we are saying that every point is reachable as long as we can reach that point. Let's say a point in front of your nose. That point is attainable if you can at least do it in with one orientation of your hand. Doesn't really matter what is the approach, as long as you can reach that point, it's considerable as reachable. So there's a lot of different protocols in the literature for people to make an assessment on this so-called reachable workspace. Most important thing is to get the volume, and it's a really good metric also to check whether a given device, for instance, it's working along with the human subject in a workplace environment, so to speak. We can also use those for validating, clinically speaking, to validate or to get an insight on what is the motor function of a given patient, and that's very important to note. So what we are presenting here is a new protocol that tries to really get the full volume of this reachable workspace, and getting it through a set of motions. In this case, we suggest so this work is part of a paper that it's under review for Journal of Applied Ergonomics. And the 5 tasks we propose for this experimental protocol regard the fact that for the existing protocols, they lack of spanning the area that it's close to the body. Rather, just focus on what you can reach the farthest from your body. That said, it's the equivalent of what you can do when you have your arms stretched. So it can really not give an appreciation on what you can do close to your body, and that is really very important, especially when we take the clinical environment. For someone who cannot reach their mouth to feed themselves, for instance, someone suffering from some physical impairment, it's important that we can have a protocol that can also span that area. In the end, we'll have a more complete volume. The existing protocols, they have been done resorting to machinery, to some auxiliary devices, but also to use kinematic biomechanical models just to span. So using the joint ranges of motion and from there extrapolate. This one here allows you to really measure the full volume. And after you collect all these 5 motions, what you do is that you use the track of a point in your hand, as I explained before, and by gathering all those points in the 3D space around the human torso, with the center in the shoulder joint, you gather all of them, and afterwards you resort to alpha shapes algorithm to get the non-convex shape of that cloud, so to speak, that volume. So you might ask, what is the alpha shape? First of all, so if we think of a set of 4 points, and if you think of creating a mesh, in this case, it's a very specific case, is called the Delaunay triangulation. What the algorithm does is that it will create a mesh in such a way that it will try to maximize the minimum angles within the triangles of that same mesh. And as we can see down here, after we have this kind of diamond-shaped mesh, what we see is that if we take the convex tool of that point set, we are looking at the convex outer shape of that diamond, so to speak, and that's the equivalent of grabbing a rubber band and just positioning it around this set of points, and it will conform to those points on the outermost side, and that's a convex shape. However, if we're looking for something like non-convex in the case of the upper extremity, we really need to look into other ways of getting that non-convexity. In that case, what the alpha shape algorithm does is it will act like a carving circle that will eliminate all the edges on the mesh, starting from the outside, that cannot be circumscribed by that circle of a predefined radius that we define, the predefined radius that we choose. So in the end, as I'm showing here, you will end up with the non-convex shape that it's shown on the right side, and it has a non-convex shape, as you can see, 2 concave faces. So after collecting, performing that reachable workspace protocol and gathering all the points, we tried an assessment on which we would perform this assessment for 4 different load cases. That said, one of them consisted of not having any weight on the hand, and 3 other cases where a subject was carrying a dumbbell with a given weight and with increasing load. So we collected the information from 10 subjects, and here I'm just showing you the example for 1 subject. And as you can see, as the load increases, we start getting a more hourglass-shaped reachable workspace volume, and that's the important part for the evaluation, and that allow us to realize that the reachable workspace is rather a measure of strength, because it also varies across different individuals. So on the left side here, you can see this plot with all the shapes of the reachable workspace. For each one of the 10 individuals, we can have 3 different views, so that you can get a better appreciation on the shape. And on the right side, we see the volume for each one of these clouds. And as I said before, as the end payload increases, we'll also see a trend of decreasing volume. And we can also see that trend also varies across different subjects. Of course, they have different payloads in their hands, but this really gives us an insight on the dependency of the reachable workspace on strength, and we probably can take advantage of that in terms of its applicability for model validation. So the question that we tried to ask to answer and that we asked ourselves was: is it possible to predict? So are the models, our musculoskeletal models, good enough to predict the reachable workspace just by, let's say, calibrating them better, resorting to some subject-specific data, namely in this case resorting to dynamometric data? What we did was to perform 3 measurements across 12 different directions. So in the end, this sums up to 36 measurements for a given subject. And we performed the motion, so a maximum voluntary contraction, against the dynamometer attached to a strap. And as you could collect kinematic data on these values, on these postures and on the dynamometer, we could position them in space and then perform an inverse dynamic analysis for each one of these 36 different measurements. So the model we resort to is a right upper extremity model that comes from the standard standing model. It is capable of 8 degrees of freedom, as I'm showing here: 3 for the sternoclavicular joint, 3 for the glenohumeral joint, and 2 for elbow flexion and pronation. Wrist motion was disabled in this case because it was not so relevant for to answer our question. The models were scaled using the length math fat scaling law, which takes into account not only the weight but the height of the subject, and it's able to estimate the fat content of each segment, which allow to redefine the pre-calculated strength of the muscles in the model that we are using for a given subject. So it's a little bit of subject specificity. However, it might not be good enough, and that's something that we are also showing here today. Each one of these muscles, so the musculoskeletal model comprises 140 muscle elements, and all of these are 3-element muscle model or heel-type muscle models. The min-max polynomial criteria was used. I apologize, there's a 3 here. It's supposed to be an infinite. The min-max polynomial criterion will try to delay fatigue as much as possible. That means that if there's 3 muscles to contribute to a given static equilibrium or to a given motion, they will be recruited equally until all of them get all overloaded and they cannot produce force anymore. Well, in the physiological point of view, so to speak, because the model the antibody modeling system can handle that. And the 1-step 10 length calibration was used. So what we decided to do to make this a simple approach, we, instead of going too deep on the complexity of the 3-element muscle model, as you know, it depends on many different tuning variables such as slack length and nominal strength. We decided to assume that the tendon slack length that is defined through the 1-step calibration was fair enough, good enough, and so we only decided to try to come up with a solution for making adjustments in these models such a way that we only decide to affect the nominal strength. So that will be the equivalent of this cyan curve that I'm showing here. As the nominal strength goes up or down, so does the curve, this belly-shaped curve changes. And the optimal muscle fiber length was also predefined in the antibody modeling system. So it's very important that to perform this analysis that you save the calibration values for these predefined variables such as tendon slack length on your models, and then that every time you perform an inverse dynamic analysis, you just need to read in those values, these subject-specific values. Otherwise, the computation takes much longer because you require to calibrate the model each time, and that's not what we're aiming for here. We should save some time. That said, we try to multiply the nominal strength that the model obtains after scaling it using the standard length math fat scaling law for each one of the subjects. And what we did was to create 18 design variables for our optimization problem, on which we will group muscles, and we will pre-multiply these factors to each one of the nominal strength that was already assigned to each of the muscle elements. As you can see here, our F0 now, instead of being only the contribution of the length mass fat scaling law, we will have a joint strength factor that will pre-multiply. However, for muscles that contribute to more than one type of motion, it's we should take into account that we need to account for the contribution of a given muscle. Let's say the long head of biceps, it contributes for both elbow flexion and shoulder flexion. That said, both factors for the group of elbow flexors and for the group of shoulder flexors should be pre-multiplied to the nominal strength value of the long head of the biceps. And so, using this procedure, what we were aiming at in our optimization problem was to define a problem that will try to use those 36 measurements strength measurements we performed on the lab using the dynamometer. So we applied the external force of the read by the dynamometer on our model along the longitudinal axis of the segment in question where the brace was attached. And so using a least squares approach, we try to minimize the difference between the overall muscle activation that the model gives us for a given inverse dynamic analysis, and that will be translated in is that for each one of the angles. So let's say we have elbow flexion here, as you can see, and we have three different measurements. For those three different measurements, the muscle element, so the muscular tendon unit, will be varying its length. That would correspond to three different points in this curve. And that would mean that we would like our design variables to be able to adjust these points here in the curve, such a way that for every of those 36 measurements we performed, we would expect to get 100% muscle overall maximal muscle activation. And that means that at that given point in time, and that also corresponds to reality, all the muscles are doing their maximum if we have 100% activation. All the muscles that can help counteracting that external force will be fully activated. However, this problem is quite complex when we have 36 different measurements and we have 18 variables. So the way to minimize the complexity of the problem is to resort to surrogate modeling. In this specific case, the box backend design allows you to only assess very specific minimal set of points in our design space, and we can get a fair approximation or an analytical function on how each one of these overall maximal activation functions for each individual strength measurement. How does it respond to different changes, to little perturbations in each one of those 18 design variables we defined? And of course, it's 36 measurements, and with the amount of samples that we need, it's for each iteration we'll have 22,000. So it is a lot of samples, and every time you do this, this is depressing in the sense that every time you do this, you need to call anybody to perform typically takes 15 seconds for the inverse dynamic analysis to be ready, because you also need to remember you need also to reassign the values for the tendon-like length and all those other variables that were previously defined. So that's the way we have to economize time, is to resort to these surrogate models. This looks bad, but it's better than in the case that if we were not resorting to it. So that is exactly the problem, because for the optimization step, we resort to a global optimizer called complex algorithm. Pardon me. And this box backend design, what it allows us is to minimize the computation needs to still have a good answer on the final optimum that we are looking for. And therefore, once we achieve convergence, we can have a good set of variables that will likely have a better performance than the model, the musculoskeletal model that was just standardly subject-specific scaled, so to speak. So previously, the simulations were taking nearly a month, but after resorting to surrogate models, we could reduce the computational time just to a few days, and that's very positive. So if we look into each one of these 36 measurements, so if we individualize them rather than looking at the overall objective value of our objective function, and if we compare the length math fat scaled only model against the new one that we just optimized, so the one that we made more subject specific, so to speak, as you can see here, the model has a little bit of problem for some of the postures so the length math fat scaled model, so the not so subject specific, tends to fail a little bit on saying that for that given posture with those conditions, those strength, those external loads applied to the body, it's not the muscles are not able to attain 100% muscle activation. So in fact, they attain more than 100%, meaning that this might tell us that the models are weaker than our real subjects. However, if we disregard these outliers, and if we just zoom in and look at this region I highlighted here, what you can see is that the box plots on the left side showing these little statistics for how the length math, so that not so subject specific model is working, we can see that there's a lot of overactivation across all of those directions that we previously defined, those 12 directions. For each one of these box plots, we aligned the 3 measurements of each one of the subjects, and then we computed the median and the quartiles. So on the right side, you have all the box plots for the optimized model, and it's really nice to see that the optimizer is doing his job, in a sense that typically the median value for all those same measurements seen from the optimized and more subject specific model are capable of attaining nearly 100% activation. So that's a plus. However, if we look into these joint strength factors, when they are pre-multiplying each one of the nominal strength values that are obtained in the literature, we kind of get a bit surprised in the sense that some of these muscles are required to have, let's say, 10 to 20 to 30 times the strength that they have in the literature. We've seen all the studies, and we know that these values sound a bit unreasonable. Not a bit, but too unreasonable, and we were expecting something like 3 times in that order of magnitude, bigger than the literature values that are in the antibody modeling system. And this might have to do with the tendon like length problems, but I'll come back to that later. So if we look into so now we have a scaled model. Is it possible? So now that we optimize our model, it is more subject specific than the other previous method we had, like this. Let's call it default, this length math fat scaled model. Now that we have this optimized one, is it possible? How can we use it in order to benefit and take advantage of it to predict the reachable workspace? How would we do that? So if we think of the same points that we collected previously for the kinematic, that protocol assessment for the reachable workspace, since those motions were performed in a very slow pace, such a way that dynamics were not influencing how people was reaching this or another point. What we define is that we discretized all of those frames for the collective all the points for the 5 different tasks, and we discretize them and perform an inverse dynamic analysis for each one of those. And what happens is that if a given posture is attainable from the modeling point of view, if the posture is attainable, that means that the overall muscle activation in our musculoskeletal model should be at most 1. That means that all the muscles that need to collaborate, so to speak, need to work to attain that posture, to attain that static equilibrium, are being recruited within their capabilities, their strength capabilities. And those are the blue points you're seeing here. However, if we get postures in which the overall muscle activation is greater than 1, that means that the muscles need to do more than what they're capable of, and of course that physiological doesn't have any meaning. Therefore, we define those as red points, and we take them out, and we don't take them into account for drawing a reachable workspace. So using the standardized version, the not so specific version of our musculoskeletal model, even though it was geometrically scaled for each one of the subjects that we're looking for. In this case here, we have an example for how does the model predict the reachable workspace in terms of attainable positions from the overall muscle activation point of view. In black, the black dots that you see here are the really motion captured points that were collected before, as I explained. And what we did was to use those in the, as you can see on the dark blue colored shape volumes. We use those to generate the reachable workspace from the modeling perspective. And as you can see, as load increases, the volume is really compromised. So it gives us a look that gives us the impression that the models are very weak compared to our real subjects, as these clouds are not able to fit within the black dots that was the real motion capture data. However, let's assume for a second that our model was very, very strong, and for such conditions in which the reachable workspace is not complete, let's say for an heavy load case, what will happen is that the reachable workspace experimentally is smaller. So if a model was really strong, what would happen? What we would eventually see is that all the points would be attainable. That would mean that we would have a perfect match. But would that be true? Would the model be completely right? So in order to assess that, what we also did, and as you can see here, these light blue range, these light blue clouds that I'm also showing there, the shapes, light blue shapes. What they're done is that if we use the same, if you perform the inverse dynamic analysis, the simulations, using all the points that were collected during the no payload case tasks, and we perform an inverse dynamic analysis on each one of those, and then we assess if the model is too strong, then we would expect that we are able to see how big this light blue shape gets in relation to the dark blue shape. And that's very important because it will tell us the story that if the model is very strong, then that light blue will be much, much bigger than these black dots that we are seeing here. But overall, what we want to show is that by only using the standard methods we have currently available in anybody, the models are not capable to predict the reachable workspace as experimentally seen. However, and this is very important, if we take the more subject-specific one, so the one with the joint strength factors, the JFSs, what we see is that the model can now do a bit better, can perform better when compared to the not so personalized model. And that also, we can also see here that as the load increases, so does decrease the volume, but we can still see a better approximation against the experimental data. And that's very good, which by showing us that the model is performing better. So if we think of an evaluation way to compare this not so good with the little better scaled version, and if you look at the original volumes that we collected for the experimental data, and we assess the intersection between those experimental volumes and the volumes that we got from these new simulations, what we see is that on the left side we have the length met fat scaled model, so the weaker model. We can see here that these points do not follow so well the trend, the volume trends of the load cases, while the joint strength factor, once we can see through the lines when we connect all the points that they better follow the trend, which once again shows us that potentially this is a better way to so it's a good method or a good tool to be used for model validation. However, we should bear in mind some very important things. We know that the length met fat scaled only are generally weaker. So we really need to take into consideration maybe to collect more data points, or even to optimize the tendon slack length and other values such as the pronation angle and optimal fiber length eventually. But the thing that we should bear in mind is that the one-step calibration procedure, what it does is that it uses a previously known posture on which we have let's say a guarantee that the muscle will work, the muscles are working at their optimal fiber length. So what happens is that if it's the scenario that the muscles get short, let's say the slack length is shortened, what will happen most likely is that our muscles are working on outside their let's say comfortable zone, so the range in which they can produce a lot of force. So what also happens is that the passive force, as these muscles get stretched, the passive force goes up quite quickly. As this passive force is also dependent on the nominal strength, as these parameters adjust, so adjust is the passive force. And in the end, what we think that these models did, so even though they are not physiologically correct, what the models did was that they looked for minimizing the trade-off between the passive stiffness that was being produced and by the antagonists and the activation that was required or the force that was required to attain a given posture. And that's why they really fitted better to the data, to the strength data that we measured. So we are probably upon an overfitting problem over here. However, we should not disregard the potential of the reachable workspace as seen as a validation tool for musculoskeletal models. And of course, more work should be done later, and we should see whether this holds or not. So with that said, thank you very much for your attention. I'm open to questions. I just would like to give you a small briefing on another thing we are working on, and eventually we'll have another webinar on this. So the compact scissors device was also created within my project, and the solution that you're seeing here recently got an innovation award from the Wearable Robotics Association, a conference that took place last month in Scottsdale, Arizona, and we won the Innovation Challenge grand prize, first place. And what I want to show you here is the fact that when we came up to the concept, what we did was to use the antibody modeling system before even manufacturing the first prototype. So the one you're seeing there on your right side, this very compact solution, shoulder mechanism, we by far only manufactured one mechanism, and that was done because that was possible because we performed some kinematic simulations within antibody modeling system. And as you can see here, now you're familiarized with these clouds, these shapes of the reachable workspace. The green one represents what the subject can do without having the orthosis on him and without any payload. And the red one, as you can see, the darker shade, represents what the subject can perform while wearing the device. So we were just looking at kinematics in this case to prove that this solution is not only very, very compact, but its novelty is that it is singularity free within the workspace of the shoulder joint. And this is a really good improvement for future exoskeletons and also other medical applications. If you're curious, just Google or go to YouTube and check CXD compact scissors device. We are also on Twitter and on Facebook, so drop by and give us a like, please, if you're interested, and we can get in touch for future collaborations. Thank you once again, and have a good night.
Great. Thanks for that great talk, Miguel. So this webcast is going to be available on our YouTube channel. You just need to go onto YouTube, search for Anybody Technology, and you'll see this this skeleton staring back at you. We also have, if you're interested in figuring out more publications within this field of research, you can go and check out the publications on our homepage, and these are there are many categories of publications, so you can go in there and sort out the ones that you really want. As for future events where you can find us, we actually have a PhD course that is just in a couple of days. Now this is fully booked, but I didn't put it over here just to show off. These courses actually keep happening from time to time, and I would just like to bring to the attention of those of you out there who probably want to come down here to Aalborg and spend some time with researchers from the group that Miguel comes from to learn some. I'm not sure, is it 2 or 3 days, Miguel, the course?
I think it's 3 days.
Okay.
Maybe.
Yeah, so it's a 3-day course on which introduces musculoskeletal modeling right from the basics.
Maybe
so,
it's 4. I'm not sure.
Yeah, something in that range. But yeah, so just keep a watch out. We'll announce these in future webcasts, and you can also keep a track of the Anybody Research Group homepage on the university website. If you're going to be at the Qualisys user group meeting in Gothenburg in May, again, we'll be there as well. If you'd like to meet and brainstorm solutions that you are working on and where you think anybody could be of help, just send us an email at sales@anybodytech.com. And then finally, we have this is probably still quite some way away, but we have the World Congress of Biomechanics, where we'll have a booth, as well as we'll have a live session over there with Exens, where we'll talk about a combined pipeline for outdoor motion capture. So this is, of course, in Dublin, Ireland.